Welcome back. In this study, we're going to be looking at Newton's second law of motion, which relates acceleration to force. If you put a force on a mass, you can accelerate that mass. The bigger the mass, the harder it is to accelerate. So there is a relationship there. As one goes up, the other comes down. As one goes down, the other comes up. So we'll see that there's a relationship there. We're also going to be looking at weight, what is weight, and also friction. How does friction oppose motion? So let's get started. So the first thing that Newton was able to write down was that the acceleration of an object is based upon the force exerted on that object. So if you were to take a basketball and throw it to someone, okay, the basketball at the beginning is not moving at all. So in order for that ball to leave your hand with any kind of speed, you'll have to accelerate it from 0 to whatever speed that you want it to go. Remember that acceleration is the change in speed in a certain amount of time. Well, the way that you make that ball go faster than 0 is that you shove that ball. You have to have a force on an object in order to cause an acceleration. Now, as soon as that ball leaves your hand, you can exert no more force on it. The only thing that's acting on the ball is gravity. There's the force of gravity that the earth is pulling on the ball, and all that'll do is send the ball down towards the ground. If you want a force, you're going to maintain a force with your hand pushing on that ball, and as long as you are exerting a force, you are changing its velocity and you're making it accelerate. So Newton was able to write this down, that the acceleration is proportional to the force. So if you push harder, you're going to make that ball go faster as it leaves your hand. If you push it slower, you're going to have a lower acceleration. Also, the mass has something to do with it. We'll see that in a minute, that the mass, the more massive a ball is, to throw a basketball is easier than throwing a medicine ball that you use in weight training. So a corollary, or something that's connected to this idea, is friction. So if two things are shoving together, no matter how smooth they might appear, they're going to have microscopic bumps on them, and those bumps are acting like Velcro. So there's a stickiness to it, or a resistance to motion. So you don't have something called a frictionless surface. Even ice has a certain amount of grit to it, and that's the way that you can actually, if you've ever gone ice skating, that's the reason you can actually push yourself off, because there is a little bit of friction there. It's very low, and that's why you can glide around. Your socks on the floor is slicker than your tennis shoes on the floor. And so friction depends on the object that is grinding against each other and the surface area of that object. Okay, so the friction on a crate on a wooden floor is less than on a rough floor. The rougher it is, the more that the ridges are going to catch each other and resist friction. So another corollary is weight. Now, your mass is how much matter you contain. What stuff is in you, okay? You've got a certain volume, whatever the volume of your body is, and you also have a certain amount of matter or material in it, okay? Some more than others, I know, I'm trying to work on that. In any case, when you put a weight or a mass in a gravity field, the gravitational pull of the earth on that mass is called weight, right? So your mass is going to be in kilograms. You weigh a certain amount of kilograms. In America, we're the only country in the entire planet that uses the old British system. The British don't even use the British system. They used to use pounds and miles and stuff like that. We still do, for whatever reason. We're stubborn. But the metric system of mass is in kilograms. And a kilogram is your mass, and it will be the same no matter where you are. So if you are on the moon, your mass is exactly the same. You don't change the amount of stuff you have by being at a different location. But the moon is 1/6 the size of the Earth, and for that reason, it pulls 1/6 as strong. So you don't have as much weight on the moon as you would on the Earth. If we were on Jupiter, which is multiple times more massive than the Earth, then you would have many, many times heavier weight, even though your mass doesn't change. Now, we've already talked about inertia. Inertia is that resistance to changing in motion. An object in motion stays in motion. An object at rest stays at rest unless acted upon by another force. That's the basketball that you have to shove in order to throw it outside of your hand. So something that has more mass has more inertia. So mass is actually a measure of the inertia of it, and it has nothing to do, gravity doesn't affect it, it's just the amount of stuff that you have. The greater your inertia, the greater your mass. So it's easier to throw a ping pong ball than it is to throw a bowling ball, okay? So kilogram is the unit of mass. Your weight is going to be the force of gravity acting on that. We'll see that the force of gravity is about 10. So it's going to be 10 times your kilogram mass. And the unit that we use in America is the pound. You are so many pounds of weight. So this is a review slide. So mass is fundamental. It's something that's based upon you. Your weight is based upon where you are. So the more massive the planet you're standing on, the more it's pulling, the heavier your weight. The less massive, the less it would pull, and your weight would change. So your weight is based upon the gravitational pull. So if you were floating out in space with no gravity pull at all, you would be weightless, but that doesn't mean that you don't have mass. So here's the first math that I'd kind of like you to look at. If you want your kilogram mass, you're going to have to divide your weight in pounds by 2.2. Think of it as just dividing in half. All right, so if you weigh 100 pounds, you're going to have a 50 kilogram mass. If you weigh 200 pounds, you're going to have a 100 kilogram mass. Your weight in the metric system is in newtons, okay, named after Isaac Newton, and essentially it's 9.81 meters per second squared is the acceleration of gravity of the Earth. You can think of that as 10, just round it to 10. So it's going to be 10 times your kilogram mass. So if you weigh 50 newtons, if your mass is 50 kilograms, then your weight is going to be 50 times 10, which is 500 newtons. 500 newtons is your gravitational pull on your mass. Now, in Newton's formula, we see that in order to accelerate a mass, you put a force on it, okay? But if you increase the mass of an object with the same amount of force, you're going to reduce the acceleration. They're related inversely. So the bigger the mass, the smaller the acceleration would be. Okay, so think of it, you throw a baseball as hard as you can and it lands somewhere. You throw a softball as hard as you can and it'll land somewhere. It's a little bit bigger. And then you throw a bowling ball as hard as you can and it won't go as far, because the more mass of the object, the more force it requires. So if you're throwing as hard as you can't add any force with your arm, and the acceleration is not going to be as much, and so the distance won't be as much. So mass is actually an opponent to acceleration. The more mass, the less acceleration. The smaller mass, the greater acceleration. Think about, that's why you put huge guys on the offensive line on the football team, because you want as much as you can to push back the others. And it's the reason why you put big guys on the defense, because you have to have, it's harder to accelerate them than if they're bigger. It's just the way it works. So 3 cheers for Isaac Newton. He was the first fella to actually put all this down into a book. Maybe not the first to think about these ideas, but the first to get credit for them. So in more formal language, this is what Newton wrote down. The acceleration produced by a net force on an object is directly proportional to the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. I'll show you in a second that I think of it in a much simpler way. If you use math, believe it or not, it's a lot easier than using English when you're trying to understand relationships. So here's an equation that may be a little easier. The acceleration on an object is the force that you push on that object divided by how much mass it has. Okay? There's another way you could say it. You could say that the force on an object is equal to the mass of that object times its acceleration. So the second one, you see the acceleration is just solving for A. So you have F, which is your force, and the m is in the way, so you divide by m, and so you'd have acceleration equals force divided by mass. So you could solve, since this is an equation, you can solve for any of these three. You could solve for mass by saying it's the force divided by the acceleration. You could solve for force by saying it's the product of the mass and the acceleration, or you could solve for acceleration. It's the force divided by the mass. Pictures are helpful. So I've got a force, it accelerates a brick. So I'm pushing at a certain amount. If I push twice as hard, it's going to speed that brick twice as much, which means that it has twice as much energy when it leaves my hand, it has twice as much speed when it leaves my hand. That acceleration went from stopped brick to moving brick, okay? If you double the mass, okay, and you push with one hand, with that, whatever that force is, you're not going to accelerate it as much. You're going to accelerate half as much. If you double your force and double your mass, then that would be the same as if you same as the first picture, where you have a force and a mass. So if you doubled one and doubled the other, then your acceleration would be the same. So that is what you play with. That's the ideas that you play with as you go up and down. What if I make it heavier? Is it going to accelerate as much? Well, what if I use more force? Will it accelerate more? Those are your questions. This, I think, is the most surprising of all the slides. We saw that most people think that if you make something heavier, it's going to fall faster. And there is some logic there. Your brain is not stupid. That is a good thought, because if you have more mass, you're going to have a greater attraction towards the earth. Your gravity is higher, okay? The pull, or your weight is higher. The pull of gravity on that mass is more the more massive you are, okay? So a heavier object gets pulled stronger. But there is the other law of Newton that has to be considered, and that's inertia. An inertia simply said every time you have a mass, you will resist change in motion. If it's stopped, it wants to stay stopped. And it's hard to get it to go. If it is going, it's hard to get it to stop. Okay, so if you have, in the case, two packages falling, one with a mass and one with a double mass, okay, and that's twice the weight, that means you're going to have twice the gravity. So the second one should fall faster if that's the only consideration. But the second one has twice the mass, and so it's twice as sluggy, if you want to think of it that way, to change. It doesn't want to start speeding up. It wants to stay the same speed it is. So it's harder to move, it's harder to accelerate a double-sized object for that reason. And you see, they both cancel out. So when two packages are dropped, it does not matter what their mass is. They will fall at the same rate, because they're pulled at different amounts, but they also have different inertias. Now, to getting your head around that, that's pretty cool, because I would have fallen into the same problem of thinking that a heavier object would fall faster. So did Aristotle, one of the smartest men that ever lived. Never thought it all the way through and figured that it would fall faster. It took Galileo 1,500 years later to actually do some experiments to see, no, that's wrong. And it was inertia of Galileo that became Newton's first law. So even though it was Galileo that first thought of the idea of inertia, it was Newton who realized what that meant. He realized the significance that two objects, no matter their mass, will fall at the same acceleration, because their masses compared to the Earth is so puny. It doesn't matter if you have 1 pound being dropped, or 2 pounds, or 100 pounds. When the mass of the Earth is zillions and zillions of times bigger than that, you end up with a common acceleration. So we're going to see that G, or gravity, is a specific case of A. A is your acceleration, and since we live on this Earth and we're not planning on going anywhere else, we think of a specific case, G, and we're going to see that G is 9.81 meters per second every second. So if something is falling, every second it's getting 9.8 meters per second faster. Okay, so 9 meters, okay, meters about 3 feet-ish, okay, so that means 27 feet in a second. That's what a meter, that is what 10 meters per second would be. It's about 30 feet, it's actually 32 feet in a second. Well, that's the speed, 32 feet a second faster every second. So if something falls out of an airplane, it's going to go in 1 second, it's going to go 32 feet per second, and then twice that in 2 seconds, 3 times that in 3 seconds. And so G is a common idea of gravity, and it was Newton who had this idea that it doesn't matter what you weigh, your gravity is going to be the same. Now, if you remember what I told you about friction, when two objects grind against each other, there is microscopic stoppage, if you want to think of it, of motion, and friction will eventually slow anything down. Okay, you're not going to go forever unless you're in a frictionless environment, maybe like space, perhaps. Okay, but if you're falling in the air, you do have air molecules, which is matter. Now, they're very light because it's in the gas form, and there's very little volume and very little mass, and so there's not a ton. You can walk through the air, but you start having lots of air hit you, and it's almost like a wall. Okay, you've all stuck your hand out of the car window, and you can feel the opposition of those air molecules against your hand just going 50 miles an hour. Well, as you are going faster and faster and faster falling, okay, you've got two forces on you. You have the force of gravity pulling you towards the earth, and you have a backwards force caused by the bumping of the air molecules in on this package as it's falling. Okay, so you have two objects, or two forces, one going up, one going down. You're going to see that the air friction going up is never going to be 100%. So you don't have the coyote that just kind of falls halfway and stops. It doesn't work that way. But it does oppose. So air friction means you don't fall as fast as you would have fallen if you were in a vacuum. So this brings us to another thing that Newton came up with, and that is the idea that unless you're in a vacuum, you cannot totally fall at 9.81 because you do have some opposition from those air molecules. There is some slowing down. So even if you drop a basketball to the ground, you are going to have a little bit of slowdown as that ball falls due to the air that's in the room. And the bigger the surface, the more that it would resist air. That's why that if you drop something round like a marble and something equally as massive, same amount of mass, but that would be, say, flat like a large piece of cardboard or a piece of cardboard with the same weight as the marble, the cardboard is not going to fall as fast because it's catching the air more. So the frontal surface area, the one that's hitting the air, and its speed, okay, will determine how much of free fall it is. Free fall really is thought of as an object falling in a vacuum in a gravity field. Now, I've had friends that have jumped out of airplanes. You'd have to push me out of an airplane if you wanted to get me out of one. And that would cause, I would have fight you all the way through. But in any case, if you do, say, jump out of an airplane, and you do have, the faster you fall, the more that your friction works, okay? The more that the air is bumping into you, and the more the air is actually slowing you down. There is going to be a place to where you're not going to get faster, okay? So imagine falling out of the airplane, and you're going 0 initially. After 1 second, you're going 10 roughly with a little bit of air friction subtracting, and then 20 meters per second, and then 30 meters per second, and then 40 meters per second. You're getting faster and faster and faster. Well, the faster you go, the more friction that you're experiencing from the air, and eventually you're going to get to the point where the force of gravity is equaling the air resistance. Okay, the air resistance goes so much that it's equaling the force of gravity. Now, that doesn't mean you stop, because you're still falling at a speed. You may be going 50 meters per second through the air, but you don't get faster. Okay, so A person truly, if they didn't have, this is called terminal velocity of a jumper or a parachutist. Terminal velocity means you fall, and then after a while, you're going at a constant speed. You don't keep getting faster after a certain amount of fall. Okay, you fall for a few hundred yards, half a mile or whatever, and then eventually your speed equalizes, and that's called terminal velocity. And it's because gravity is being equally opposed by the force of friction. Essentially, gravity is being canceled out. And this is the term for it. Terminal speed is how fast that you're going to go because you're not getting faster. Terminal velocity is the same. I assume that you're falling down. Okay, so terminal velocity means as you're falling and air is hitting you, eventually the gravity pull, which is making you faster, is opposed by the friction of the air, and you stop getting faster. It's called terminal velocity. Okay, I've tried to explain this already. Skydriver jumps, the weight's the only force acting on it, and then eventually air resistance starts picking up, and now it's slowing you down. The faster that you fall and the more you're going through the air, the more air resistance, and eventually gravity is opposed by this air resistance, and you stop getting faster. You've reached your terminal velocity. On the moon, in Apollo 11, I think it was Apollo 11, Neil Armstrong dropped a feather and a hammer. And since there's no atmosphere on the moon, there is no air on the moon, it is a vacuum. And since it's a vacuum, the feather wasn't opposed by the air molecules any more than the hammer was. And on television, in front of everybody, he dropped them and they hit the ground at the same time. Just like Galileo had deduced when he first did the cannonball experiments off of Pisa Tower, after reading one of Aristotle's books that says that heavy things fall faster. Okay, so this is a lab thing. I used to have one of these. It's a coin and a feather, and you take a pump and you pump all the air out of the glass tube, and when you turn it over, they'll slam onto the bottom a plate just at equal times.